Planets are moving in ways that should be impossible. Across the cosmos, worlds drift with a purpose that gravity alone cannot explain, hinting at engines we do not yet understand. By the end of this journey, you will see our solar system not as a fixed clockwork, but as one small part of a wildly dynamic and mysterious universe. We will explore why a rogue gas giant orbits at an impossible tilt, and what invisible force pushed an interstellar visitor through our neighborhood. How many of the rules we take for granted are simply waiting to be rewritten? The first crack in our celestial understanding appeared not with a planet, but with a visitor. In 2017, telescopes detected a strange object tumbling through our solar system. It was the first confirmed traveler from another star, and scientists named it Oumuamua. Its path was a straight line out of the darkness, but its speed was the real puzzle. As it hurtled away from the sun, it accelerated in a way that gravity alone could not explain. It was as if an unseen hand was giving it a gentle, steady push. This was non-gravitational motion, a phrase that has since sent ripples through the world of astronomy. For centuries, our view of the heavens was built on the work of Isaac Newton. His laws of motion and universal gravitation painted a universe of predictable orbits where every action has an equal and opposite reaction. But Oumuamua did not follow the script. Its extra acceleration forced a profound question. What else besides gravity could be moving objects through the void? Experts like Dr. Avi Loeb suggested possibilities that ranged from the natural to the extraordinary. Perhaps the object was outgassing like a comet, releasing material that acted as a natural thruster. Yet no visible coma or tail was seen. Maybe the pressure of solar radiation was pushing on an object with a bizarrely large surface area. Or perhaps, and this is where the mystery deepens, we were witnessing something entirely new. The search for answers led scientists to consider forces we can barely measure, like the subtle tug of dark matter or interactions with a hidden ocean of energy in space itself. Oumuamua was a warning. It told us that the rules we learned in school are incomplete. The stable clockwork of our solar system might be the exception, not the rule, and this single strange object opens the door to our first great mystery. Oumuamua's silent passage was our first clue, but it is far from the only one. Far beyond our solar system, a true planetary rebel defies every expectation. This is HD 106906b, a gas giant with 11 times the mass of Jupiter, adrift in a cosmic exile. Its home is not a cozy orbital neighborhood, but a staggering void. It circles its star at a distance 730 times greater than the span between Earth and our Sun. At that range, the star would be little more than a bright pinprick in a perpetual black sky. Its orbit is not a neat circle, but a stretched, tilted ellipse, a path that should be impossible for a planet of its kind. How did it get there? Standard planet formation theories tell us that worlds coalesce from a spinning disk of gas and dust, ending up in relatively flat, orderly orbits. This giant does not fit that story. It is an outsider, a cosmic drifter that either formed in a completely different way or suffered a violent history. Astronomers are left with two compelling and unsettling possibilities. Perhaps it was born much closer to its star and then experienced a gravitational catastrophe, a slingshot event so powerful it was hurled to the outer darkness. The culprit could have been a close encounter with another massive planet, a gravitational tug of war that sent it flying, or maybe a passing star intervened, its gravity plucking the world from its original cradle and setting it on this new, lonely course. The other possibility is that it never truly belonged to the system at all, that it was a rogue planet born in solitude that was captured by the star's gravity as it wandered by. Either scenario paints a picture of a far more chaotic and dynamic universe than we once believed. The stable clockwork of our own solar system might be a fortunate anomaly. The mystery of HD 106906b forces a profound question. If a planet this massive can be thrown so far off course, what other invisible forces are sculpting the cosmos, silently rearranging worlds without any conventional engine in sight? That strange, silent push on Oumuamua was a whisper from the void, a hint of forces we are only beginning to sense, but the mystery runs deeper than a single object's path. Astronomers have since spotted a second interstellar wanderer, Comet Borisov, which behaved far more predictably like a classic comet with a visible tail. This stark contrast makes Oumuamua even more perplexing. Why did one visitor follow the rules while the other seemed to break them? The leading natural explanation suggests Oumuamua could have been a shard of solid hydrogen ice. In the cold depths of interstellar space, a block of hydrogen could form, and as it neared the sun, the heat would cause the ice to turn directly into gas, puffing away invisibly and providing the thrust we observed. Yet, this theory has its own problems, as such a fragile hydrogen iceberg would likely have disintegrated long before reaching us. This is why the more extraordinary idea, proposed by Harvard professor Avi Loeb, captured the public's imagination so powerfully. He suggested Oumuamua could have been a light sail, a piece of advanced technology from another civilization using the pressure of starlight for propulsion. While most scientists favor a natural origin, the very fact that such a bold idea must be considered reveals how deeply this object challenges us. Oumuamua's true legacy is not a single answer, but a profound question mark. It underscores the frustrating limitations of our telescopes. We saw it only for a few weeks as it sped away, a faint pixel of light already receding into the darkness. We simply did not have the tools to get a clear look, to analyze its composition, or to solve the puzzle definitively. This accelerating anomaly forces us to expand our definition of what a natural celestial object can be. It pushes the boundaries of known physics, reminding us that our catalogue of cosmic phenomena is still woefully incomplete. What other strange travelers are passing through our neighborhood, unseen and unexplained, simply because we do not yet know how to look for them? Far from the wandering planets and interstellar visitors, a different kind of mystery pulses from a distant sun. KIC 8462852, known as Boyajian star, flickers like a dying light bulb in the cosmos. Its light doesn't dip in the regular, predictable rhythm of an orbiting planet. Instead, it plunges by staggering amounts, up to 22%, as if colossal, uneven shapes are drifting past it, blocking its light in a chaotic dance. This is not the signature of a simple world. A planet the size of Jupiter would only dim a star like this by about 1%. What then could possibly cast a shadow this vast? The search for an answer has led to some of the most imaginative theories in modern astronomy. Perhaps a vast, fragmented swarm of comets surrounds the star, their dusty tails intermittently blocking our view. Yet the sheer amount of material required defies belief. This is why some scientists, like Professor Jason Wright, floated a more staggering idea. Could we be seeing the silhouette of a megastructure, an immense array of solar collectors built by an advanced civilization to harness the star's energy? While compelling, most astronomers seek a natural explanation, and one of the most intriguing involves an invisible push on the star itself. observations reveal that Boyajian's star is not only flickering erratically but also slowly, steadily dimming over years. This long-term fading could be a crucial clue. It might mean the star is not just being orbited by strange objects, but is itself on the move. The star could be drifting through a vast, dark cloud of cosmic dust, its light gradually obscured. But what force could set a star in motion? The culprit may be completely invisible, a dense knot of dark matter, or the subtle gravitational tug of a nearby black hole we have not yet detected, could be nudging the entire system, altering its position relative to our line of sight. This case ties the mystery of erratic light directly to the mystery of unexplained motion. It suggests that the strange things we see around a star might be symptoms of a deeper, darker influence. The true architecture of this system may be built from components we cannot see, where dark, unseen masses are as important as the shining suns they shepherd. Boyajian's star is a profound reminder that the cosmos is full of shadows, and what we don't see may be actively shaping the universe we can. The universe is full of shadows, but it also contains systems of intricate precision. Far from the chaotic flicker of Boyajian's star, a different cosmic arrangement presents its own enigma. Huddled around a faint, cool dwarf star are 7 Earth-sized worlds, known as the TRAPPIST-1 system. They orbit so close to their star that a year on the innermost planet passes in just over a single Earth day. You could fit the entire system comfortably within the orbit of Mercury around our own Sun. At first glance, it appears to be a perfectly scaled model of a solar system. Yet, detailed observations reveal that these worlds are not holding perfectly steady orbits. They drift, showing subtle orbital variations that gravity alone struggles to fully explain. The immense tidal forces from the star, the same kind of gravitational pull that causes ocean tides on Earth, are certainly at work stretching and squeezing these planets. But mathematical models indicate this constant tug of war is not powerful enough to account for all the migration we see. It is as if an invisible hand is gently nudging these worlds, adding another layer of motion that our current understanding of physics cannot completely capture. What could this hand be? Scientists are exploring forces that are far more subtle than gravity. Perhaps powerful magnetic interactions are at play. The star TRAPPIST-1 is a turbulent, active body, and its magnetic field could be interacting with the magnetic fields of the planets themselves, creating a complex push and pull. Another possibility is the stellar wind, a constant stream of charged particles flowing from the star, which could act like a steady breeze on a sail, gradually altering a planet's path over millions of years. This tightly packed system has become a perfect natural laboratory, allowing us to watch how multiple planets interact under extreme conditions. The drifting worlds of TRAPPIST-1 teach us a profound lesson. Even in a system we think we understand, the story written by gravity may have entire chapters missing, filled instead by the quiet, persistent influence of forces we are only just learning to measure. Drifting in the profound darkness between stars, a world travels utterly alone. This is PSOJ 318.522, a rogue planet that belongs to no sun. It is a gas giant 6 times more massive than Jupiter, yet it is not tethered to any star's gravity. It is a free-floating voyager, moving through the cold void with no light to warm its skies and no day to break its eternal night. The very existence of such a world shatters a fundamental assumption that planets must always orbit a parent star. Its motion is its own, a silent journey through the galaxy, and its origin is one of astronomy's great debates. How did it get there? Was it born in the chaos of a stellar nursery, a failed star that never gathered enough mass to ignite, destined from the beginning for a life of solitude? Or does its past hold a more violent story? The most compelling theory is that this lone giant was not always alone. It may have formed in a young solar system, only to be violently evicted. A gravitational slingshot, a too-close encounter with a sibling planet, could have flung it out into the deep like a stone cast from a sling. The evidence for this dramatic exit lies in its speed. Its motion does not perfectly align with any known group of young stars it appears to be associated with, suggesting it received an extra push, an acceleration from a close encounter with another massive object. This single world forces us to reconsider the cosmos as a place of both creation and destruction, where planetary systems are not always stable, and where gravitational chaos can exile a world forever. The enigma of Perseus J3 18.522 is a haunting one. It makes us wonder just how many such lone wanderers are drifting in the darkness, unseen and unknown. Current estimates suggest there could be billions of these rogue planets in our galaxy alone, a hidden population of worlds forever traveling between the stars, their motion a silent testament to the dynamic and often violent processes that shape our universe. The star Fomalhaut blazes in the southern sky, a brilliant beacon surrounded by a stunning ring of icy debris. For years, astronomers watched a tiny point of light within that ring, a world they named Fomalhaut B. It was a planet caught on camera, orbiting its star in a way that seemed to defy simple explanation. Its path was not a gentle circle but a stretched, eccentric ellipse, and it appeared to be moving with unexpected speed. Then something truly bizarre happened. The planet simply faded away. Observations with the Hubble Space Telescope revealed the pinpoint of light dissipating, growing larger and fainter until it vanished into the darkness of space. It was not a planet dying, but a planet disappearing from existence because it may never have been a planet at all. The leading theory now suggests we witnessed the aftermath of a colossal cosmic collision. What we thought was a super-Earth perturbed by gravitational forces was likely a vast, expanding cloud of fine dust. This cloud was created when two large planetary bodies, perhaps massive asteroids or protoplanets, smashed into each other. The dust cloud, reflecting the star's light, mimicked the appearance of a single, moving world. Its strange, fast trajectory could have been the natural expansion of this debris, not the orbital motion of a solid body. But this explanation only deepens the mystery of its movement. What force could have orchestrated such a violent crash? The culprit is likely hidden within the complex dynamics of Fomalhaut's debris disk. Unseen planets, their gravity weaving through the disk of ice and rock, could have created gravitational resonances. These are like invisible patterns of push and pull that can destabilize orbits, steering objects into catastrophic paths. The apparent motion of the dust cloud was a ghostly echo of this unseen gravitational dance. The case of Fomalhaut B is a profound lesson in cosmic illusion. It reveals how the circumstellar environment, the intricate interplay of gravity, dust, and hidden worlds, can create phantom planets in our data. It forces astronomers to ask a humbling question. How many other detected exoplanets are not solid worlds, but fleeting clouds of dust, their apparent motion a mere shadow of a far more violent and transient reality? But the ghost of Fomalhaut B is not the only world whose path is being rewritten by unseen forces. Around the young, brilliant star Beta Pictoris, a colossal gas giant named Beta Pictoris b orbits within a vast, sprawling disk of dust and debris. This planet is a teenager in cosmic terms, and like a teenager, its path is not entirely straight. Its orbit is tilted, warped out of alignment with the main debris disk that circles its star. This misalignment is a glaring clue that something is wrong with our simple picture of this system. The planet is not moving as a solitary king in its domain, but as a piece in a complex gravitational puzzle. Something or someone is pushing it. The primary suspect is a hidden world, a sibling planet that has so far eluded our detection. This unseen giant could be gravitationally tugging on beta Pictoris b, pulling its orbit into this strange, inclined path over millions of years. But there is another, more subtle force at play. The star beta Pictoris is incredibly luminous, and it bombards its nearby giant planet with an intense flood of radiation. This light doesn't just illuminate the world, it physically pushes on it. Scientists theorize that this radiation pressure could be stripping material from the planet's upper atmosphere, creating a kind of natural rocket effect. While incredibly faint, this constant push could, over immense timescales, contribute to the planet's drifting path. The mystery of beta Pictoris b forces astronomers to stop thinking in terms of single causes. Here, the planet's motion is not the result of one engine, but a chorus of influences, a combination of gravitational nudges from hidden neighbors and the persistent, ethereal pressure of starlight itself. This case teaches a vital lesson about cosmic complexity, where the simple dance of two bodies is often an illusion, masking a far more intricate and crowded ballet. These colossal gas giants huddle dangerously close to their suns, worlds that should not exist where we find them. We call them hot Jupiters, and their very presence is a cosmic contradiction. Born in the cold outer reaches of a star system, where ice and gas are plentiful, they have somehow completed a grand pilgrimage to the inner sanctum, orbiting their stars in mere days. The question is not just how they moved, but what powerful, unseen force compelled such a dramatic journey. The standard story involves a young star's protoplanetary disk, a swirling sea of gas and dust. As a giant planet forms within this disk, its gravity can create spiral waves that act like a brake, slowly sapping the planet's orbital energy and causing it to spiral inward over millions of years. This process is elegant, a gentle cosmic drift, yet for many hot Jupiters, their orbits tell a far more violent tale. They do not trace perfect circles, but are stretched into eccentric ellipses, and they are often tilted at sharp angles to their star's equator. This is the signature of a chaotic past. A gentle drift through a smooth disk cannot create such orbital madness. These wild paths point to a history of gravitational upheaval, a game of planetary pinball where close encounters with other giant worlds acted as a slingshot, violently hurling them toward the star. Some may have been sent on such a rapid, chaotic plunge that they nearly fell into their sun, only to be saved at the last moment by the star's own tidal forces, which circularized their orbit into the scorching close embrace we see today. In the most extreme cases, astronomers even speculate that a star could capture a rogue planet, a lone wanderer from the interstellar dark, pulling it into a tight orbit and creating a hot Jupiter not from its own system, but from the depths of space. This mysterious migration forces us to accept that the serene order of our own solar system is just one possible outcome. Planetary systems can be dynamic, even violent, places where worlds are not born in their final resting spots, but are pushed and pulled by engines of gravity and chaos we are only beginning to map. While hot Jupiters are scorched by their stars, another world experiences the opposite extreme, a solitude so profound it defies belief. The planet known as 2 Mass J 212681 is locked in an orbit of almost incomprehensible scale. Its year lasts close to 1 million Earth years, and it drifts at a distance from its star over 7,000 times greater than the span between our Earth and Sun. At such a remove, the star would be indistinguishable from the background of other stars, a faint, cold dot in a perpetual night sky. This is not a planetary system as we know it. The gravitational thread tying this world to its sun is so impossibly thin that its very existence challenges our definition of what a family of planets can be. How can such a tenuous bond possibly hold? The leading theory is that this world was not born here but was captured. It may have begun its life as a rogue planet, drifting alone through the galaxy, until a chance encounter with this star, or more likely a pair of stars, gravitationally ensnared it into this vast, lazy orbit. But this capture scenario is itself a mystery. The gravitational tugs required to gently trap a wandering world without flinging it away entirely or sending it crashing into the star are incredibly delicate. The influence of a binary companion star, or perhaps the distant, unseen gravity of a passing star in the cluster, could have provided just the right nudge. The enigmatic glide of 2 Mass J 212681 forces us to ask what truly keeps a planet bound to its star. At this distance, the star's gravity is almost vanishingly weak, a whisper in the void. Other forces must be at play to maintain stability across such an immense gulf. The subtle, cumulative gravity of the galaxy itself, or the dark matter halo that permeates the system, could be providing an invisible scaffold that helps lock this distant world into its path. This lone planet demonstrates that the boundaries of a solar system are not fixed walls, but porous and dynamic borders, constantly reshaped by the gentle, collective pull of the entire cosmos around it. Deep within the quiet glow of a red dwarf star, a world teeters on the edge of possibility. Gliese 581g, a planet whose very existence has been fiercely debated, represents a different kind of mystery. It is not a giant defying gravity, but a small, rocky world that might hold liquid water, a potential haven for life. The controversy around it begins with its detection. Astronomers have found other planets in the system, but the data for Gliese 581g is a subtle whisper buried in stellar wobbles, a signal so faint that some teams claim to see it while others see only noise. If it is real, its path is a delicate dance at the mercy of its siblings. Orbiting within a compact system of multiple worlds, it is subject to a constant gravitational chorus. The gentle, repetitive tugs from its neighboring planets can create complex resonances, a rhythmic pushing and pulling that can gently heat the world's interior and subtly alter its orbital path over millions of years. This is not a violent slingshot, but a persistent, rhythmic nudge that rewrites the planet's trajectory. Another force may be at work, one born from its star's embrace. The red dwarf Gliese 581 is an active star, and its gravitational pull creates intense tidal forces on a close orbiting world, flexing its crust and heating it from within. This tidal heating could be so powerful that it drives volcanic activity and even causes the planet's atmosphere to expand. If the atmosphere puffs outward, the pressure of the star's light itself could push against this larger, more tenuous envelope. It is a minuscule effect, like a solar breeze on a cosmic sail, but over astronomical time, this could result in a measurable drift, an indirect motion caused by the star's energy reshaping the planet itself. The mystery of Gliese 581g is ultimately about stability. To be habitable, a world must maintain a stable orbit within a temperate zone for billions of years. If unseen forces are constantly tweaking its path, that delicate balance could be easily lost. Finding this world and understanding the subtle engines that drive it forces us to look beyond simple gravity. It challenges us to consider how a planet's own evolving nature, from its molten core to its shimmering atmosphere, can become a quiet, unconventional engine in the dark. Another silent giant wanders the interstellar dark, known only by its catalog number, CFBDSIR 2149-0403. This object is a ghost, a planetary mass body drifting utterly alone, and its very nature is a puzzle. Is it a true planet ejected from a solar system, or is it a failed star, a brown dwarf that never quite ignited? The distinction matters because its origin story is written in its motion. Astronomers trace its path back to a young group of stars called the AB Doradus moving group, a family it seems to have been born with, yet its speed and trajectory are slightly off, as if it received an extra, unexplained push after being cast out. This misalignment is a crucial clue, pointing to an unknown acceleration event in its deep past. Perhaps it had a close encounter with another massive object within its original system, a gravitational kick that sent it flying with more velocity than a simple ejection would provide. Or maybe the interstellar medium itself is playing a role. Infrared observations reveal this drifter possesses a cloudy, complex atmosphere. As it moves through the thin gas and dust that fills the space between stars, that atmosphere could be acting like a sail. The drag from this tenuous material could be slowly breaking its motion, while in other scenarios, the pressure of starlight on atmospheric particles could provide a tiny, continuous thrust. These subtle interactions are forces we rarely consider for planets, but for a lone voyager, they become significant engines over cosmic time. The enigma of CFBDSIR 2149-0403 ultimately challenges our need to put everything in a neat box. It exists in a hazy borderland between planet and brown dwarf, and its journey suggests the galaxy may be filled with such ambiguous, solitary wanderers. Each one is a silent testament to the dynamic and often violent processes that shape solar systems, their lonely paths holding untold stories of gravitational chaos and cosmic ejection. Sometimes the most profound mysteries are born from harmony, not chaos. In the Kepler-36 system, two wildly different worlds are locked in an impossibly close embrace. One is a rocky super-Earth, a colossal version of our own planet. The other is a gassy mini-Neptune, a world with a thick atmosphere and no solid surface. They orbit their stars so near to one another that their paths bring them within just 1.2 million miles of each other, a distance 5 times closer than the Moon is to Earth. At that proximity, their gravitational pull is immense, a constant, rhythmic tug of war that slightly alters their orbits with every pass. This is not a random drift, but a precise clockwork dance. Their orbital periods are in a tight resonance, meaning for every 7 orbits the inner planet completes, the outer one makes exactly 6. This resonance creates a predictable pattern of gentle pushes and pulls. Yet, even this elegant gravitational explanation may not be the full story. The intense closeness suggests other, more subtle engines could be at work. The gravitational squeezing between the two planets, combined with the pull of their star, likely generates fierce tidal heating within their cores. This is the same kind of friction that drives the volcanoes on Jupiter's moon Io, but on a planetary scale. This internal heat could be causing the mini-Neptune's atmosphere to swell and churn, changing its density and shape in a way that subtly affects its gravitational field. It is as if one dancer in the pair is constantly changing their own weight, forcing the other to adapt their steps in response. Furthermore, if either world possesses a strong magnetic field, the interaction between those fields and the star's powerful wind could add another layer of complex force, a magnetic nudge on top of the gravitational pull. The Kepler-36 system reveals that planetary motion is not always a solo performance dictated by a star's gravity. It can be an intricate duet where the planets themselves become engines for each other's motion, their interiors and atmospheres actively participating in a ballet that gravity alone cannot conduct. A quiet star named HD 2794 hosts a delicate family of small, rocky worlds. These are not gas giants on wild orbits. but Earth-sized planets that should, in theory, trace predictable, steady paths around their sun. Yet they do not. Minute observations reveal subtle wobbles in their motion, tiny orbital deviations that act like a faint, persistent whisper of an unseen presence. The radial velocity method, which measures the star's subtle dance as planets tug on it, detects these tugs, but the gravitational pull we can account for from the known planets does not add up to the full story. Something else is there, pulling gently on the entire system. What kind of force could nudge multiple planets at once without revealing its source? The most tantalizing hypotheses point to influences that are completely invisible to our telescopes. Perhaps a dense, localized clump of dark matter is drifting through the system. This mysterious substance, which does not emit or reflect light, could exert its own gravitational influence, subtly warping the paths of the planets as it passes. Another possibility is a distant, massive object orbiting far beyond the known worlds, a cold gas giant or even a small brown dwarf whose faint gravity is just strong enough to make its presence known by disturbing the inner planets. This is a ghostly influence, a gravitational signature without a visible body. The mystery of HD 2794 demonstrates the incredible sensitivity of our modern instruments. We are now detecting anomalies so slight they would have been utterly invisible just a generation ago. Each unexplained wobble is a potential doorway to a new understanding of what shares the cosmos with us, encouraging astronomers to consider that the quietest solar systems may be the ones with the most profound secrets, their serene orbits gently guided by invisible hands. Tau Ceti E appears to be everything we have been searching for, an Earth-sized world orbiting within the gentle, life-giving region of a sun-like star. But its motion holds a secret, a faint wobble in its orbit that betrays an unseen complexity. This is not the violent chaos of a hot Jupiter, but a subtle, almost imperceptible drift, as if the planet is navigating a crowded and invisible sea. The star Tau Ceti is known to be surrounded by a massive disk of icy and rocky debris, far more dense than the Kuiper belt in our own solar system. The collective gravity of this countless swarm of objects could be gently tugging at the planet, creating a persistent background hum of gravitational noise that nudges its path over time. Yet, even accounting for this, some models suggest the wobble is too pronounced. Could other, more delicate forces be at work? The pressure of the star's own light, constantly streaming outward, exerts a tiny push on the planet. For a massive world, this effect is negligible, but for a smaller, rocky body, it might be just enough to contribute to a long-term orbital drift. Another possibility lies within the planet itself. If Tau Ceti E is geologically active, with volcanoes spewing gas into space, this outgassing could act as a minuscule thruster. Each puff of atmospheric material ejected from the planet would impart a tiny amount of thrust, slowly altering its trajectory in a way that mimics a gravitational pull from an unseen source. These potential engines are incredibly weak, but over millions of years, their effects can accumulate into the wobbles we detect. This mystery forces astronomers to confront the immense challenge of a noisy stellar environment. Disentangling the faint signal of a planet's non-gravitational motion from the gravitational buzz of a debris disk and the inherent activity of the star itself is like trying to hear a single whisper in a roaring stadium. Tau Ceti E represents a critical frontier in the hunt for a second Earth. To truly know if such a world is habitable, we must first understand every single influence on its journey, no matter how small. Its gentle wobble is a warning that even the most promising Earth-like planets may be dancing to a tune we have only just begun to hear. The whisper from Oumuamua has not faded with time, it has only grown more complex. A new chapter in its mystery suggests the object was not a hydrogen iceberg, but one made of solid nitrogen. This exotic substance, familiar to us as the main component of our own air, behaves differently in the deep freeze of interstellar space. As a chunk of nitrogen ice approached the Sun, the heat would have caused its surface to sublimate, transforming directly from a solid into a gas without ever becoming a liquid. This stream of invisible nitrogen vapor puffing away from the surface could have acted as a natural and stealthy thruster, explaining the steady push we observed. The theory is elegant, solving the puzzle of why no dusty comet tail was visible. Yet, this solution demands its own set of extraordinary conditions. To match the observed acceleration, Oumuamua would have needed to be composed of an incredibly pure slab of nitrogen, a type of iceberg rarely, if ever, seen in nature. Its bizarre, flattened shape would also be a relic of this composition, a shape carved away over millions of years by cosmic radiation. This very specificity keeps the door open for other possibilities. Perhaps the answer was not a chemical thruster, but a magnetic one. Some researchers point to the solar wind, that constant stream of charged particles flowing from the Sun. If Oumuamua possessed an unusual magnetic field, its interaction with this wind could have created a measurable force, a magnetic drag or push that nudged it along without any outgassing at all. The enduring debate over this one object is a powerful lesson in cosmic science. A single, silent traveler has generated a spectrum of hypotheses, from the exotic natural to the potentially artificial, each one a different model for how a celestial body can propel itself without a conventional engine. This unresolved puzzle is now the driving force behind a new era of mission planning. Space agencies are actively designing spacecraft that could lie in wait, ready to launch on a moment's notice to intercept the next interstellar visitor. The ultimate goal is to get close enough to finally see what we are dealing with, to solve the propulsion puzzle not with theories, but with direct evidence from another star. The silent, drifting worlds we have encountered hint at forces we cannot see. But what if the greatest influence is also the most abundant? The universe is not mostly empty space, it is mostly dark matter, an invisible substance that makes up over 80% of all mass. For decades, we assumed this dark matter only interacted with the cosmos through gravity, a ghostly presence that shapes galaxies but does not touch the planets within them. Now, a radical idea is challenging that assumption, the dark matter drag hypothesis. Imagine a planet like a ship sailing not through empty water, but through a sea of invisible, treacly mist. This is the proposal that dense, localized clumps of dark matter could exert a subtle, non-gravitational drag on any world moving through them. It would be an incredibly weak force, like a whisper against a mountain, but over millions of years, this persistent, gentle braking could slowly sap a planet's orbital energy, causing its path to decay or its speed to change in ways that gravity alone cannot explain. This could be the answer to why some planets, particularly those in the outer halos of galaxies, display unexpected motions that seem to defy the gravitational pull of visible matter. Theoretical physicists like Dr. Lisa Randall have explored models where certain types of dark matter particles do more than just warp space. They interact weakly with normal matter through other fundamental forces. If this is true, then a planet passing through a dense knot of this material would experience a tiny amount of friction, a cosmic drag that would be almost impossible to detect directly, yet would leave its signature in the long-term evolution of an orbit. The evidence for this remains elusive, buried in the slight anomalies of distant worlds. This hypothesis pushes at the very boundaries of physics, forcing us to consider that the unseen majority of matter in the cosmos might not be a passive backdrop. It could be an active, dynamic ocean, its invisible currents silently steering the worlds we see, a fundamental engine of motion hiding in plain sight all along. Magnetic fields may be the hidden architects of our solar system. Long before planets settled into their current orbits, they were seeds within a swirling disk of gas and dust, a nursery bathed in the powerful magnetic field of a young, active sun. This field did not sit idly by. It was an active participant in the construction process, a silent force capable of moving entire worlds. The principle at work is the transfer of angular momentum, a way for the spinning star to push material outward or pull it inward. Think of it like a cosmic conveyor belt where magnetic field lines act as invisible arms, gently shoving gas and dust and the young planets forming within them to new locations. This process could have guided the gentle, early migration of giants like Jupiter, setting the stage for the entire architecture of our planetary neighborhood. But for an individual world, a more direct force could take hold, the Lorentz force. If a young planet possesses a charged upper atmosphere, its particles become like tiny sails caught in the stellar magnetic wind. The interaction between these moving charges and the powerful magnetic field of the star creates a physical push or pull. It is an electromagnetic engine, one that requires no rocket fuel, only the fundamental laws of physics playing out on a colossal scale. The evidence for this is written in the wild youth of other stars. We observe intense magnetic activity around stellar infants with field strengths that can dwarf our suns. In these frenetic environments, the magnetic propulsion of protoplanets could be a dominant force, rapidly hurling them across vast distances or locking them into resonant orbits. Yet, its full importance remains one of the great unresolved debates in planetary science. How do we measure the strength of a magnetic field that vanished billions of years ago? Can we detect its faint signature in the orbital patterns of ancient exosystems? This mystery forces us to see the early cosmos not as a placid pool of dust, but as a dynamic and electrified workshop where invisible magnetic hands were just as important as gravity in placing the planets on their paths. The universe is not silent but resonates with the echoes of ancient violence. When two black holes spiral into a final, desperate embrace, their collision sends tremors through the very fabric of space-time. These are gravitational waves, ripples that travel at the speed of light, stretching and compressing everything in their path. For a planet drifting in the void, the passage of such a wave is an unimaginably subtle event. It might change the distance to its star by less than the width of a single atom. The effect is so tiny it seems utterly insignificant. Yet, over millions of years, as countless waves from countless cosmic mergers sweep through a solar system, these minuscule nudges can accumulate. It is a form of cosmic Brownian motion, a gentle, persistent buffeting from the most powerful events in the universe. This idea transforms our view of a planet's path from a solitary journey to a dance choreographed by distant cataclysms. The orbit we see today could be the sum of every black hole collision and neutron star merger that has ever sent a shiver through the galactic neighborhood. This gravitational wave ripple effect creates a profound connection between the local and the cosmic. A planet in a quiet, stable system is not an island. Its motion is subtly linked to the death cries of stars in far-off spiral arms, its path slowly rewritten by energies released billions of years ago. Detecting this influence is a staggering challenge, a whisper buried beneath the roar of gravitational pulls from nearby stars and planets, but the search itself reframes our place in the cosmos. We are not just observers of these distant events, we are participants, our local celestial clockwork gently adjusted by the universe's most extreme phenomena. This enigma forces a humbling realization. The steady orbit of a world is not a guarantee, but a temporary balance, subject to the faint, cumulative push from the darkest and most energetic corners of creation. Even the vacuum of space is not truly empty. It seethes with a phantom energy, a quantum foam where particles and their opposites wink into and out of existence in a relentless, chaotic dance. These are virtual particles, and their fleeting lives create a subtle pressure known as the Casimir effect. In laboratories, we can observe this force. Place two perfectly smooth, uncharged metal plates extraordinarily close together in a vacuum, and they will be pushed together by the sheer pressure of this quantum activity outside the gap. The question then becomes a staggering one. Could this same phantom pressure operating on a cosmic scale act as a gentle, continuous thrust on something as vast as a planet? Quantum vacuum thrust theory dares to explore this possibility. It suggests that in regions of intense gravity or high energy, near a neutron star or within a dense nebula, the quantum foam could become more active. This heightened activity might create a minute imbalance in the vacuum pressure surrounding a world, a tiny push from one direction that is not perfectly balanced by a push from another. Over billions of years, this imperceptible force could, in theory, contribute to a planet's drift. It is a speculative idea, a whisper from the frontier of physics, but it forces a profound reimagining of what space is. We are asked to stop thinking of the void as a passive stage and to start seeing it as a dynamic medium, a quantum ocean with its own currents and pressures. While the effect would be vanishingly small for any single object, its universal and constant nature means it could be a background force acting on everything, everywhere, all at once. This concept is not about a single engine moving one planet, but about the very fabric of reality participating in a silent, universal propulsion. The quantum vacuum remains one of the greatest unsolved puzzles in science. Is it truly a source of potential motion, or merely a fascinating theoretical curiosity? Unlocking this mystery would mean we have finally begun to understand the true, seething nature of nothingness itself, and how that nothing might quietly steer the stars. The void between stars is not a perfect emptiness. It is a diffuse ocean of hydrogen gas and microscopic dust grains, a medium so thin it defies earthly comparison. Yet for a planet traveling alone for millions of years, this near-nothingness becomes a tangible force. This is the drag of the interstellar medium, a form of cosmic air resistance acting on the grandest of scales. Imagine a rogue planet, a world without a sun, drifting through this tenuous fog. Its immense gravity pulls on the sparse gas, gathering a thin shroud of atmosphere around it. As the planet moves, it rams into the interstellar material ahead, creating a bow shock, a heated wave front like the prow of a ship cutting through water. This interaction is a constant, gentle break, sapping a tiny amount of momentum with every light year traversed. For planetary scientists, detecting this deceleration is a monumental challenge, but the clues are there. Telescopes have observed some free-floating planets glowing faintly in the infrared. This heat is the telltale sign of a compressed and heated atmosphere, the direct result of plowing through the galactic medium at tremendous speeds. The trajectory of such a world would not be a perfect straight line dictated by inertia alone. Over eons, this persistent drag could curve its path, subtly altering its course through the galaxy. It is a passive, universal engine, one that requires no internal power, only motion itself. This force transforms our view of a rogue planet's journey from a simple, lonely glide to a continuous negotiation with its environment. The very emptiness of space becomes an active participant. its subtle friction slowly but inevitably rewriting the destinies of these lone wanderers. Io's fiery volcanoes are not born from the sun's heat, but from an invisible gravitational tug of war. As Jupiter's moon travels along its slightly elliptical path, the colossal planet's gravity stretches and squeezes its interior, creating immense friction that melts rock from the inside out. This is tidal heating, a geological engine powered entirely by orbital motion. Yet this relationship is a two-way street. The energy expended to heat Io's core must come from somewhere, and it is slowly, inexorably, siphoned from the moon's own orbital energy. This process acts as a subtle but persistent brake, a non-conventional engine that is gradually altering Io's path around its giant parent. Now, scale this phenomenon up to an entire solar system. Imagine a rocky super-Earth orbiting perilously close to its red dwarf star. The star's gravitational pull locks one face of the planet in a permanent blaze of daylight, while the other side freezes in eternal night. This is tidal locking, but it is far from a stable embrace. The same gravitational forces that created the lock are now flexing the planet's mantle, heating its core to a molten frenzy and driving world-spanning volcanic eruptions. This internal furnace does not just reshape the landscape, it rewrites the planet's destiny. The energy lost to this constant geological turmoil is drawn from the planet's orbital momentum. Over millions of years, this transfer can cause the world to migrate inward, drifting closer to the star in a slow, gravitational spiral. In other cases, complex interactions with sibling planets can pump energy into an orbit, increasing its eccentricity and stretching it into a more elliptical path. This creates a powerful feedback loop where the changing orbit intensifies the tidal heating, which in turn further alters the orbit. The planet becomes both the heated and the heater, its own internal geology, an active participant in steering its cosmic journey. This mystery reveals that a planet's path is not just a line drawn by gravity, but a living record of its internal fire, a dance between the world it is and the orbit it keeps. A star's wind is a relentless gale of charged particles, an invisible river flowing outward into the void. This stellar wind carries momentum, and when it strikes a planet, it delivers a tiny, continuous push. For a massive world like Jupiter, this force is little more than a whisper against a mountain. But for a different class of planet, this whisper can become a meaningful nudge over cosmic time. Consider a super-Earth with a puffy, extended atmosphere, a world whose gaseous envelope is loosely bound by its own gravity. The pressure from the stellar wind acts directly on this atmosphere, like a constant breeze pushing on a vast, ethereal sail. This can slowly strip the outer layers of the atmosphere away, but it can also exert a force on the planet itself, a slight but persistent thrust that alters its orbital speed. The effect is amplified around active young stars, which erupt with ferocious stellar winds, or aging red giants, whose winds are dense and powerful. In these extreme environments, the cumulative push on a vulnerable planet could be enough to cause detectable orbital drift, gently migrating the world inward or outward over millions of years. This is a propulsion system that requires no fuel, only the natural output of a star and the specific characteristics of the planet it embraces. It transforms a star's activity from a simple background condition into an active participant in planetary dynamics, a silent engine sculpting orbits through the subtle, unending pressure of its breath. Gravity can choreograph a dance far more complex than a simple circle. Picture a planet locked in a gravitational tango with two different partners, its orbit slowly twisting and reshaping under their conflicting pulls. This is the Kozai mechanism, a subtle gravitational resonance that acts like an invisible hand, periodically tilting a world's path and stretching it into a new shape. The process works through a constant exchange of orbital characteristics. Over thousands of years, a planet's inclination, the tilt of its orbit, is traded for eccentricity, how stretched its orbit becomes. A world on a flat, circular path can be lifted into a steeply inclined orbit, only to later fall back toward the star on a wildly elongated elliptical path. To an outside observer, this looks like a planet moving under its own power, executing a series of complex maneuvers with no apparent engine. This phenomenon is often seen in binary star systems, where a distant companion star exerts a steady, perturbing influence on the planets orbiting the primary star. Yet astronomers are now asking if this mechanism could be at work in more solitary systems, driven not by a second star, but by a hidden, massive planet lurking in the outer darkness. The Kozai mechanism provides a compelling natural explanation for some of the most baffling exoplanets we have found, like hot Jupiters with orbits sharply tilted against their star's rotation. These worlds may not have migrated inward through a gentle disk, but could have been violently flung toward their sun by the resonant kick of a distant gravitational partner. This mystery forces us to see solar systems not as flat, two-dimensional arrangements, but as dynamic, three-dimensional hierarchies where a distant, unseen object can orchestrate profound change. The real engine behind a planet's strange motion might not be on the world itself, but could be a silent conductor, light years away, pulling the strings from the shadows. Chaos is a creative force in the cosmos. Long after the dust of formation settles, planetary systems can remain volatile arenas where gravitational tensions between sibling worlds finally snap. Picture two Earth-sized planets born in the same stellar nursery, their orbits destabilized by a delicate resonance. They are drawn together not in a gentle merger, but in a cataclysm that shatters their crusts and vaporizes their mantles. In an instant, their orderly orbital dance is replaced by a cloud of incandescent debris and a few surviving fragments, now hurtling away from the impact site with tremendous velocity. This is not science fiction. It is a common outcome in sophisticated computer simulations of young solar systems. These models reveal that gravitational instabilities are a natural part of planetary adolescence, often leading to dramatic collisions or high-speed ejections. A world flung from its star becomes a rogue planet, its motion powered not by an engine, but by the gravitational slingshot of its former siblings. Its trajectory is now a permanent, unpowered glide through the interstellar void. But what of the debris left behind from such an impact? The cloud of shattered rock and vaporized metal can itself become a temporary propulsion system. As this hot, expanding debris cloud cools, certain ices or volatile compounds within it might begin to outgas, puffing away material and acting like a natural, short-lived thruster. Alternatively, radioactive elements forged in the violent collision could heat the debris, causing it to emit radiation. The sheer pressure of this radiation could provide a slight but measurable push on the entire fragment cloud. This means the aftermath of a planetary catastrophe can itself generate unconventional motion, propelling the resulting shards on new and unpredictable paths. These collision and ejection scenarios fundamentally reshape our understanding of cosmic order. They suggest that for every serene, stable system like our own, there may be another that endured a violent youth, its planets scattered, destroyed, or exiled. The lonely path of a rogue planet or the bizarre orbit of a surviving world are not necessarily mysteries requiring a hidden force, but could simply be the lasting scars from a gravitational war that happened billions of years ago. Perhaps the greatest engine moving planets is not a force at all, but a flaw in our deepest understanding. For centuries, we have interpreted the cosmos through Isaac Newton's law of universal gravitation, a framework so powerful it predicted the existence of Neptune before we ever saw it. Yet, what if this foundational law is merely an approximation, a local rule that breaks down on the grandest scales? This is the provocative heart of our final mystery, the hypothetical engine of modified gravity. The most prominent of these ideas is known as modified Newtonian dynamics, or MND. It proposes that gravity does not weaken as quickly with distance as Newton and later Einstein described. Instead, at extremely low accelerations, like those found in the faint outskirts of galaxies or in the vast spaces between stars, gravity gets a subtle second wind. It becomes slightly stronger than our standard equations predict. This single tweak was initially proposed to solve one towering anomaly, the galaxy rotation problem. Stars at the edges of spiral galaxies orbit far too quickly to be held in by the gravity of the visible matter alone. The standard solution is to invent dark matter, an invisible substance that provides the extra gravitational glue. But MND offers a radical alternative that we don't need to invent missing matter because we are simply using the wrong math for gravity. If MND is correct, its implications would ripple down to the scale of planetary systems. Those subtle orbital drifts we have explored, the unexplained motions of distant worlds or the strange paths of some rogue planets, might not require dark matter drag or quantum vacuums. They could be the natural consequence of gravity itself behaving in a slightly different way in the deep quiet of interstellar space. A planet orbiting at the extreme edge of a solar system, where the sun's pull is incredibly faint, might experience this modified gravity as a gentle, persistent nudge, an extra tug that alters its path in ways that standard physics cannot explain. This idea remains deeply controversial, as it struggles to explain all the phenomena that dark matter elegantly accounts for, such as the gravitational lensing we see in galaxy clusters. Yet its enduring power is in the profound question it forces us to confront. Are we seeing the effects of unseen matter, or are we witnessing the limits of our most trusted physical laws? This final mystery brings our journey full circle, back to the very rules we use to read the cosmos. It suggests that the most powerful engine behind inexplicable motion may not be hidden in the darkness between stars, but in the equations we have written to describe it. The true revolution may not be in discovering what is moving the planets, but in finally understanding the force that has been holding them all along. These 25 cosmic anomalies form a constellation of clues scattered across the galaxy. Each one, from the lonely rogue planet to the star with inexplicable dimming, is a piece of a much larger puzzle. They reveal a universe that is not a static museum of fixed orbits, but a living, breathing, and wildly dynamic arena. The idea of a conventional engine, a fiery rocket pushing a world along, is almost quaint when compared to the reality we are uncovering. Planetary motion is a symphony conducted by many forces, where gravity provides the main melody, but dark matter, magnetic fields, and quantum pressures contribute the harmony. Experts are now connecting these dots, using tools like the James Webb Space Telescope to peer into dusty nurseries where planets are born, and running vast supercomputer simulations to replay billions of years of gravitational history in a matter of days. Every strange wobble in a star's light, every impossible orbit, is a data point that helps refine our models of cosmic evolution. Solving these mysteries is not just about cataloging curiosities. It pushes at the very frontiers of human knowledge, promising breakthroughs that could redefine physics itself. Understanding how dark matter drag might shape a solar system could reveal the true nature of this invisible substance. Deciphering the magnetic propulsion of a young world could teach us how to harness similar forces for our own future journeys among the stars. this grand synthesis makes one thing abundantly clear. The unknown is not a void to be feared, but an ocean of possibility waiting to be sailed. Our place in the cosmos is that of the perpetual student, forever humbled and forever curious, listening for the next whisper from the dark that will rewrite everything we thought we knew. Our journey through these 25 cosmic riddles reveals a universe far stranger than we ever dreamed. Each unexplained motion, from the silent push on Oumuamua to the lonely glide of a rogue world, is a crack in the foundation of our understanding. These are not mere curiosities, they are profound challenges to the rules we thought governed the heavens. They tell us that gravity, while a powerful force, is not the sole author of a planet's path. Our models are incomplete, beautiful approximations that break down at the edges of discovery, and it is precisely at these edges, in the gaps of our knowledge, that scientific progress ignites. Every mystery is a question waiting for an answer, a puzzle that pushes our technology and our imagination to their limits. The great astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. This is the heart of our exploration. The cosmos is not a solved equation, but a living story, and we are only just learning to read its pages. So we invite you to keep looking up, to keep questioning what you see. Wonder about the dark spaces between the stars and ponder the forces that move worlds in silence. The next great revelation is out there, hidden in the light of a distant sun or the path of a wandering rock. If these mysteries have stirred your sense of wonder, join us for more journeys to the frontier. We would love to hear which of these cosmic puzzles captivated you most, so share your thoughts below.